Okay, this is the quick version of how do we combine sine and cosine curves with different phases. And where we need to start quickly is most people wouldn't be at all surprised when you add two sine curves together. So I've got a green one and a blue one that are exactly the same. Most people would expect it to give me twice as big a sine curve. That's quite normal. What people are less able to predict is what happens when I want it to play. Is what happens when you change the position of one of them relative to the other. So if I change that back, oh, that's not in right. To add phi to that. So if I now have an angle added to one of them to change its position. Now what happens when I add these together? Now a lot of people expect them to give some sort of double peak or something. What actually happens is you get another sine wave, and depending on how the phase is, you can get it to disappear to nothing, or you can get it to double in amplitude by being on track with itself. So you can actually get another sine wave from it. And that's an important result. So what we need is we can actually write this into a simpler form of A sine theta and phi, where A is the amplitude of the output sine wave, and the alpha, or the angle being added on, is referred to as the phase. Okay, both these sine curves these must have the same angle in there though. They must be the same angle for that to work, otherwise you get an effect called beating when they're quite close together. And just to remind you, the basis of this is it allows you to take a high-powered sine wave and change, using a much lower power one that's easier to control, you can actually change its phase, so you can actually make the power grid work. That's the basis of how the power grid, different generators can work on the power grid. The thing to remember and recognise from this is, well, that pattern we now know has an identity associated with it, where that is equal to cos, where it's equal to sine theta. Sorry, it's the letters are confusing me. Sine the first angle, cos of the second angle, plus to that a cos of a angle theta, and sine of the angle alpha. So that's our trig identity that we found in previous lessons. What I can do is I can multiply through by the value a to give this form, and then we compare our expression to what we have up here. So here's my sine theta. That means those two must go together to make my 4. There's my cos theta, and the other two parts must make 3. So what we actually have is a cos alpha is 4, and a sine alpha I've got my identity wrong. Cos yeah, sorry, I've got the wrong identity, haven't I? Yeah, this is sine and that one's cos. I was thinking of the cosine identity, not the sine one. So a sine alpha is 4 and a cos alpha is 3. So we can actually take the two expressions. If I square them, what we're going to get is we're going to get a squared plus sine a squared sine squared alpha plus a cos squared alpha, and recognise that those two will factor out to give us a 1, and that must equal 4 squared plus 3 squared. So we get a squared equals 25, so a is the square root of 25, which is plus or minus 5. We often get told how big the amplitude needs to be positive, so in this case we must choose a equals 5. It is possible sometimes that it would be negative, depending on what they say about the angles are needed. So you need to look at the question, come back to it and check maybe later if you can. But because of the way this has been phrased, we know these angles will come out correctly. The second part is to realise that if you do division, the a's cancel. Sine alpha and cos alpha become 10. So a sine alpha over a cos alpha. Cancel, cancel, gives us tan alpha, which is 4 over 3. And when you do the inverse tan of 4 over 3, shift tan 4 over 3, shift tan 4 over 3, tan 4 divided by 3, and that's 0.927. Radians, 3 significant figures please. If you're doing angles, always 1 decimal place is my recommendation. And what I can do is I bring this over. What we've got is, oh sorry, I haven't written the final form. So this means this can be written in the form of an amplitude of 5 with a sine curve that has been phase shifted by 0.927 radians. And we can check that using a graphing calculator. So I've put in the first part, gives me the green curve. Notice amplitude 5, it's not in a normal position for sine or cosine, and when I put in the blue one, it replaces that one. So that's how we can get that first solution. Second one, so what they can do sometimes is they'll change things around, and what I need for this one is recognising our cos theta minus alpha. So cos theta minus alpha is in a trig identity of cos alpha, cos theta, cos alpha, plus sine theta, sine alpha. The plus, because remember the cosine it swaps round, I'm going to multiply through by r, and we get therefore r cos alpha is 1 and r sine alpha is square root of 3. We can then do square both of them to give me r squared equals 1 squared plus root 3 squared. That's from doing the r cos alpha, r sine alpha, both squared, so r must equal 4. Well, sorry, square root 4. So it equals plus or minus 2, and they told us it must be positive, so r equals 2. And we can get the tangent, tan of alpha is going to be root 3 over 1. Because we're doing sine over cos, the r's cancel, so we get root 3 over 1, and that gives me, by inverse angles, the alpha, alpha, because it's in degrees and it's a special one, we need to give an exact answer. Yes, you can put it in your calculator, but it's worth recalling the exact versions of these in case your calculator can't do them. So there's my 30, 60, 90 triangle. Tangent of root 3 over 1 means that we're looking at a 60 degree angle, so alpha equals 60 degrees, and again write it out in the form they asked. So we had an amplitude of 2, with a cosine of theta minus 60 degrees. And we'll check that one. So just grab an answer. GeoGebra, I've had to tell it that the angle's all in degrees. That's what the little O is after each part. So there's my green piece. If I put the blue one on top, they're exactly the same. Okay, that's the summing functions.